Today we're going to continue our discussion on solving simultaneous equations. And in particular, I'm solving a system of two equations and two unknowns. And I'm going to be using matrices. This video is not about matrices per se. We will be using some things from matrices to help us to solve the system. I'll be covering other videos more in depth on matrices. But this is about solving simultaneous equations using matrices. So solve the following two equations in two unknowns system using the matrix inverse method. So I'll be discussing the matrix inverse method in more depth in another video. So the original system of equations is x plus y equals 7, 2x minus y equals 2, and we want to find x and y, but we're going to use matrix techniques. Now very quickly you can see that if you add those two equations together, the y's cancel out and you get x plus 2x is 3x and 7 plus 2 is 9 because the y's cancel. So you get 3x equals 9, so x equals 3, and then very quickly you can deduce that y equals 4. So already I can write the solution down quickly in my head. So xy is equal to 3, 4. So it's good to know, have a rough idea what the solution is. If you know what the solution is before you even start the calculations, that helps, because then once you get to the end, if you get the right answer, then you've probably done the correct method. Not always, but generally speaking. So it's good to know that you have the answer. If the answer is wrong, then you've done something wrong. So a general 2 by 2 matrix, we'll call it capital A, is given by A, B, C, D. So A is top left, B is top right, C is bottom left, D is bottom right. And we want to know the determinant of that. So this thing called the determinant of a matrix. So for a 2 by 2 matrix, the determinant is equal to AD minus BC. So it's just a number, sometimes written det A with square bracket or A with two vertical bars either side. So it's very easy to find the determinant of a 2 by 2. So AD minus BC. So we'll be looking at that in a minute with a specific example. And then also this idea of the inverse of a matrix. So the inverse of a 2 by 2 matrix, we call it A inverse, or A to the minus 1. So that's 1 over the determinant, so 1 over AD minus BC, times this matrix here. This matrix is the original 2 by 2 matrix, but we've just changed it slightly. So what we've done is we've swapped the A and the D around, swapped the terms in the leading diagonal, and then we've changed the signs of B and C. So we haven't moved their positions, we've just changed their signs. Okay, and then we multiply all of that by 1 over the determinant. That gives us A inverse. Now we'll be using that because we will need to know A inverse when we go to solve this system of equations. Some other useful facts to know: this thing called the identity matrix, I is equal to 1, 0, 0, 1, which is more or less 1. You multiply any matrix by I, you just get the matrix itself, it doesn't change it. Now that is technically speaking I2, but we will ignore the 2 because we're working in a 2 by 2 system, and that's pretty obvious. Okay, so when you have a matrix A and you pre-multiply by A inverse, so A inverse A equals I, which is the same as A, and then post-multiplying by A inverse. So it doesn't matter the order you do it, you're always going to get I. And then here's another little useful thing we'll be using. So matrix A times column vector x bar is equal to B, and B will be a column vector. So that implies A inverse A x bar is equal to A inverse B. That implies x bar equals A inverse B. So the A inverse A cancels out on the left hand side. You're just left with x bar. We will be using this x bar equals A minus 1b, or A inverse B. We'll be using that to solve this system. So let's go over to the system again. So that's our system. Now we want to write that in a sort of matrix kind of form. Okay, so A x bar equals B. So our A here is going to be 1, 1, 2 minus 1. Where did I get that from? Well, that's just the coefficients of x and y in this system. And they're in the exact same positions. I've basically written the system in the exact same position. So you've got x and y at the top, 1, 1, and x and y at the bottom, 2 minus 1. So the coefficients of x are 1 and 2, so that's your first column, 1 and 2, and then the y's are 1 and minus 1, that's your second column. Right? And then we multiply that by our column vector x bar. This is what we want to find. We want to find this column vector, xy. So it's going to be equal to something. It's not going to be equal to 7, 2, but it's going to be equal to something, and that's our answer. That's the solution to the system. But as I say, we need to do some matrix multiplication. We need to use this formula to find x bar. Okay, so let's go back over here. So I've got this formula here now. Okay, and 7, 2 is obviously comes from the values of the equations. Right, so therefore xy is equal to A inverse B. So now we know B is just 7, 2. So now we need to find A inverse. So A inverse is 1 over the determinant of A. And then we need to change A slightly. We need to change the terms in the leading diagonal. So we swap the 1 and the minus 1. So that becomes minus 1, 1. And then we swap the 1 and the 2 on the other diagonal. So that becomes minus 2, minus 1. So that becomes that. So 1 over the determinant times that times 7, 2. And because we're multiplying a 2 by 2 matrix by 2 by 1 column vector, we're going to end up with a 2 by 1 column vector, which will be the solution to our system. Okay, so let's work out the determinant of A very quickly. The determinant of A is equal to AD minus BC. So if we go over here again, A is 1, B is 1, C is 2, D is minus 1. So AD minus BC is 1 times minus 1 minus 1 times 2. So that's minus 3. Okay, so let's write that in. So 1 over the determinant of A is 1 over minus 3, or minus a third. Now I'm going to leave that outside the matrix for the moment, because it will be much easier to multiply these integers together than it will be if I multiply by fractions. Because if I put the determinant inside now, I'm going to have fractions in there, so I'll leave it outside for now. Okay, so how do we get this? So to multiply 2 by 2 matrix by a 2 by 1 vector, column vector, so we just apply the matrix multiplication rules. So it's row by column rules. So this entry here, so this is on the first row and the first column, because we've only got one column. So to get that, we multiply the first row over here of the first matrix by the first column of the vector. So minus 1, and then 7, 2. So you take the first entry, minus 1 times 7, plus minus 1 times 2. So that's minus 7 minus 2, so that's minus 9. And then for this one, it's second row, first column. So we take the second row here in the first column, there only is one column. So it's minus 2 times 7 plus 1 times 2. So minus 2 times 7, minus 14 plus 2. Okay, so that's minus 12. So the answer is minus a third, that's our 1 over our determinant. And then our column vector is minus 9 minus 12. And then simplify that, we get 3, 4. And that's our answer, i.e. xy equals 3, 4. So that's the solution to our original system up here. And you can check it. 3 plus 4 is 7, 6 minus 4 is 2. So there you go, guys. Very useful, very powerful indeed. And as I say, we'll be discussing matrices in more detail in other videos. We'll also be looking at 3 by 3 system. 3 by 3 system is way more complicated. There's a lot more involved in that. And there's various methods for solving those. 2 by 2 is a lot easier to solve than a 3 by 3. Okay, but I just wanted to introduce you to the idea. So I hope you enjoyed the video. Thanks for watching. Please like, share and subscribe. I'll see you on the next video.